All right. Good morning, good evening, good afternoon, whatever the time is. This is the Calc 1, what is it, Spring 2017 Exam 2. This is now my third Exam 2, and I'm starting to get the hang of some of these problems since they're kind of all the same, just a ton of derivatives and some limits. So let's go ahead and get started with number one. Um, Hey, a bunch of limits. Look at that. So, three quick-ish limits, and seeing if they equal all of these, and choosing which one of these is right. So, I looked at this one ahead of time, and I'm gonna dedicate this one to um, how to solve a lot of these limits really quickly. Like I like to call it cheesing it, how to cheese your way through some of these limits and get the answer really, really quickly, especially because we already have a couple values that it wants us to find, so we can really quickly rule out a bunch of values, and if the ruled out values are what they say here, then we know we're done. It's false. So starting with number one, look at what it's asking. This is 1 plus a really big number since it's going to infinity, and this is 1 minus a really big number. So if we sort of plug in a really big number on the top, we're going to get a 1 plus that, so this is going to definitely be positive on the top. And if we look at the bottom, 1 minus a really big number, that's going to be negative. So a positive divided by a negative is always negative. It wanted positive 4. So we know that 1 is false. A lot of these, they go really, really quickly if you know your tricks, which I'm going to hopefully teach you a ton of right now. Number 2, limit as x approaches infinity of this equals 0. Instantly I can see this is true because look at the order of the numerator and look at the order of the denominator. Numerator order is 1. This is 6x to the 1. Numerator of the denominator is 2. And if the denominator's order is ever bigger than the numerator and you're taking the limit as it approaches infinity, it's always 0. Always. Because the uh, x squared grows faster than x. If you're a computer science major, this is kind of like big O stuff, big O notation. You can kind of think of that when you're doing those. So since the numerator's order is less than the denominator, it equals 0, which it wanted. So this one is true. And finally, with number 3, the limit as x approaches negative infinity of this. Um, I believe, hold on, I actually kind of figured this one. Okay, answer key. It's that one. Okay. Uh, yeah, this one works too. So, um, well, what we just said, where x squared grows faster than x, since it's squared, it's a parabola, goes up like that. X just grows linearly like that. Um, we know that the x squared term is always going to be greater than the x term. And since it's a really big positive number minus a less big positive number, that will always be positive, a positive infinity, since it grows way faster than just x. So we know that one's right, it equals infinity, and we can see that E is our answer. 2 and 3 are true. So those were a couple hacks and cheeses that you can use to get your way through some of these limit as x approaches infinity problems. That's what they're really best for. Um, Knowing what orders mean and if they're on the top or the bottom and their growth rates, that can save you a lot of time on these 60-minute crunch exams. All right, number 2, a quick graphing identifying problem. These are pretty fun. They're little bite-sized things. So there's a couple things you can take note from the graphic gives you that you can use to figure out which one is right. The first one is the peak, the apex, which is right there in the middle on the y-axis. So when a function hits a peak, it means that its derivative at that point is 0. It hits that vertical line, or not vertical, horizontal line, hits the x-axis. So know that whatever function we have, it has to hit the x-axis right in the middle, like right there, and it doesn't hit it anywhere else because there's no other peaks anywhere on this graph. If it was something like that, it would have another peak or a trough, and it would hit the x-axis again. But we don't have that, so it only hits 0 right in the middle. And already with that, we can rule out b there, and that's the only one. But hey, we're making progress. The other thing we can do is look at the sides of it. So it looks like on the left it's increasing and on the right it's decreasing. So we know that for any one of these graphs, the derivatives, on the left it has to be positive and on the right it has to be negative. So it looks like A is out and B is also out. C, D, and E are still, up for debate. But hey, we're still making progress. What else can you use to identify this? Um, we can actually sort of think of the second derivative. So it looks like the point at which it goes from like that to that, like right in the middle there, that would be that would be a peak of the derivative. So like let's look at D here. That would be a point like that, like where the derivative hits a peak instead of the original function. So it looks like it has one right here and one right here. So that means for the derivative, it has to have a peak or a trough uh, right at those 2 points near the y-axis. And it looks like D, the one I just did, has both of those. One right there, one right there. And neither C nor E have that, so it looks like D is our answer here. All right, number 3, derivative problem. So find the derivative of f of x and then plug in 1 for x after we find the derivative. So to start with this, I think the thing it's trying to trip you up with is these like x times square root of x and x squared times square root of x. Keep in mind that square root of x is just equal to x to the 1/2. And any variable raised to one power times the same variable raised to another power is equal to just one variable with the powers added together. So if we rewrite this as f of x equals 2 over x times x to the 1/2 plus x squared times x to the 1/2, we can see that we can combine everything into 2 over x times, or just x to the 3/2 plus x to the 5/2. So now that we've smushed that all together, actually I want to do one more thing. I'm going to move this x to the 3/2 up to the top by making it negative. So this is now 2 times x to the negative 3/2 plus x to the 5/2. So there we go. That is a lot simpler to take the derivative of because it's just the exponent trick where we move it out to the front. So this now equals negative 3/2 times 2x to the negative 5/2. Negative 3/2 minus 1 is negative 5/2 plus 5/2 x times, or to the power of 3/2. So we have that now. Here, let's rewrite negative 3/2 times 2 as just negative 3, like that. F double F prime. And now we just plug in 1 for each of these and we'll get our answer. So this is equal to negative 3 times 1 and negative 5/2 plus 5/2 times 1 to the 3/2. 1 to the power of anything is still 1, so we can basically ignore those. And we get negative 3 plus 5/2, which equals negative 6/2 plus 5/2, which equals negative 1/2, I believe. There we go, C. Okay, for a second I thought I did something wrong there, but I found it. So, yeah, just a simple derivative after you get past the first part where you realize that square root of x is just x raised to the 1/2 power. Sometimes you'll have to realize that's what's going on. You don't have to do a whole buttload of derivative work. You can just simplify it right at the beginning and make your life a whole lot easier. All right, question 4. Derivative problem. Yay. Function, take derivative, plug in 3. So derivative of x squared times e to the x, this is probably a time to use the product rule where the function is a times b. The derivative is a prime b plus ab prime. So let's plug that all in, set it up. Derivative of x squared is 2x times the raw e of x plus just x squared, the raw x squared, plus the derivative of e to the x, which guess what, is also e to the x. Uh, that's that is the only function that where its derivative is equal to the original function, just e of x. Every other function, it's different. Its derivative is different. So, sorry, that's probably one function that would be neat to know for any, um, skipping steps that you might do in the future. Now we can plug in 3 for x and get our answer. So 2 times 3 is 6 times e to the 3 plus 3 squared, which is 9, times e to the 3 again. And this yields 6e cubed plus 9e cubed, which is 15e cubed. There we go. That was nice and quick. Just product rule. Skipping a step, remembering that the derivative of e to the x is also e to the x, and then plugging in and simplifying. Not bad at all. All right, number 5. Find all values for x for which the graph of that has a tangent line parallel to this line. Okay, so um, this is a multi-step thing again. So I like to work, I like to think about it backwards at first, realize what I actually need to do as a first step. So in order to find a line parallel to this, we really just need to focus on the slope, since any line with that slope will be parallel to that. So we just need to find a line with a slope of 3. And that means all we have to do is take the derivative of this and then set it equal to 3. So if we have f of x, we can just take f prime of x, which equals something, and then set that equal to 3, and then solve for all of our x's. So let us do that. Derivative of this, we are definitely going to be using the quotient rule, which is if you have a over b, the derivative of that equals a prime b minus ab prime all over b squared. Let me check I got that right. Sometimes I forget. I forget even the most basic stuff. It's crazy. But anyways, okay, I got that one right. I got it up on my computer here. So that's good. Now we just got to plug in, 2x minus 1 and x plus 1 for a and b. And we're rolling. So derivative of 2x minus 1 is just 2 times x plus 1 minus 2x minus 1 times the derivative of x plus 1, which is just 1, all over x plus 1, squared. So we have this now. Since we're not actually plugging in a value for x, I am actually going to simplify this whole thing so that we can easily solve for 3 at the end. So I'm going to do that. This becomes 2x plus 2 on the left minus 2x minus 1, which is the same as minus 2x plus 1, all over, let's see, oh, that's just a squared, so x squared plus 2x plus 1. We can simplify the top further to 4x. No, not 4x. Actually, these two x's cancel each other out. So this becomes just 3 over x squared plus 2x plus 1 equals 3. So now we're at this step. We can solve for x. I think we can start by multiplying both sides by that term, which will give us 3 equals 3 times x squared plus 2x plus 1. I'm going to move this up here. So we can cancel both of these 3's out and get 1 equals x squared plus 2x plus 1. Subtract 1 on both sides, we get 0 equals x squared plus 2x. Take an x out of both of the right, we get x times x plus 2. So we know that x equals 0 and negative 2. So there we go. A. Make sure I got that right. 5a. Cool. Got it right on the answer key. Um, yeah, so let's see, recap. Again, this is one of those multi-step word-ish problems where you have to do multiple things, figure out in which order to do them and what to do. Um, like I said, I like to think backwards, think about what it wants at the end, which is a line parallel to that. So then I thought, okay, a line parallel means it has a slope of 3, and if you take the derivative of this, that'll equal the slope, so you can just set it equal to 3 and then solve for x. So that was my thought process for that, thinking backwards. That really helps out a lot with these word-ish problems. Okay, question 6. This is a scarily simple question because usually the simple questions on exams are always like the most, not really the most complicated, just the most fear-inducing because there's always one little thing about it, one weird little unique quirk that's unlike any other question you've done in this class. But this really doesn't look bad at all. This might be the easiest question on this entire exam if you're comfortable with your unit circle. So let's draw that out. And let's make it bigger, actually. We got a lot of room for this one. So something like that with 0 and 2 pi. So we have our unit circle. Um, let's start up by figuring out like a general area where the answer of this could be. Remember, we're doing the inverse sine. So normally with a normal sine, we take an arc length that stops at a given point and then return like this length, this value here. But we need to do the opposite. It gives us some length that is, somewhere here, and then take its arc length and, trace it all the way back and figure out its length. So we shall do that by, again, we can narrow down where that vertical line is. To start, it's negative, so it's only in the bottom half here, the bottom hemisphere, I guess. Uh, Secondly, it's also in this half only because inverse sine only returns values between pi over 2 and negative pi over 2, only between those 2 points. So we know that it's in this quadrant right here. I think it's the fourth quadrant they call it because it goes 1, 2, 3, 4 like that. That looks like a pizza. Anyways, I know it's down here. Now we can actually figure out specifically which value it is. Um, there's not really, I forget the way they kind of teach this to you, but uh, it's just really helpful to memorize your unit circle and the three kind of key values here. There's pi over 6, there's pi over 4, and there's pi over 3. Actually, these are all negative because it's down like that. And then negative pi over 2 on the bottom. Those are like the three key arc lengths that are down here. And hopefully you remember that these are all, that's negative 1/2, that's negative root 2 over 2, and that's negative root 3 over 2. That's what all of those are. Um, and yeah, this is exactly what we're looking for. So our answer is negative pi over 3. Uh, God, crap. I really wish there was a easier way to explain that to you. There's probably some way you could like construct a triangle and then like use Pythagoras to figure out like with calculations what the value would be, but I don't know how to do that to be honest. So that's the best way I can explain it if you like know your unit circle, which is very, very useful to know for calculus. All right, question 7. This is officially the halfway point on this entire exam. Uh, just a derivative. Find f prime of x, which is derivative of that. So looks like we'll need to do the quotient rule at the start. Remember when we have a divided by b and we take the derivative, that gives us a prime b minus ab prime all over b squared. So we have that. We just plug in our a and our b and we get, okay, a prime the derivative of negative sine x is negative cosine x times the bottom minus the top times the derivative of the bottom. So derivative of 1 is just 0, so we can ignore that. Derivative of cosine is negative sine. we have our top all divided by 1 plus cosine squared. I'm not going to expand the bottom, not just yet. Maybe because I just see this 1 plus cosine x on the top, and I think there might be a case where on the top we'll have a 1 plus cosine x, and we can like cancel out that or something. So just in case, I'll keep it at that. If we need to expand it later, we'll do so. All right, so let's factor out all of this. Not factor out, just simplify it and multiply and FOIL and whatnot. So the top becomes negative cosine x minus cosine squared x, and then minus sine squared x. So that's our new top, 1 plus cosine x all squared. What to do now? Um, I'm going to make it a little simpler. I'm going to change all of these minuses on the top to pluses and positives, and then make the whole thing negative. So it's kind of like we just multiplied the whole top by a negative and then added another negative, so nothing really changed. Okay, I see what we do now. So you might recognize that this here, sine squared plus cosine squared, that equals 1. That's called a trig identity. So there's a couple of them. The most common one is sine squared plus cosine squared equals 1. So we can replace all of that with just 1. So this becomes, sorry, where was I? Cosine x plus 1 all over 1 plus cosine x all squared. So now you can see I was right in not simplifying this because we have two like terms on the top and the bottom. So we can simplify that to just 1 over 1 plus cosine x. Looks like it wants us to sort of distribute the 1 up to the top, and we get c. Let me double check that's right. 7 is c. Boom, we got it. So recap, quotient rule to start, and then remembering the trig identity here. Okay, can I remember the others? I cannot remember the others off the top of my head. You could just Google the 3 trig identities, and you'll find the 3. They involve like tangent and secant, cosecant, whatnot. So I don't know if you need to know those right now. Maybe just this one for now. But in the future, especially if you take Calc 2 and 3 and whatever, yeah, you need to know your trig identities. So maybe it's good to learn those now, I guess. All right, question 8. Immediately, I never like seeing like the other trig values like secant and cosecant and cotangent. Hate working with those. So the immediate first thing I'm going to do is I'm going to rewrite this in terms of sine, cos, tan. I think that'll make it easier. So secant is just 1 over sine. No, 1 over cosine. Sorry. I always think that because they both start with s. But anyways, cosine. So this is really just 1 over x times cotangent of 3x times cosine x. And then this cotangent, so that is equal to cosine over sine. So that itself is equal to cosine over sine, but it's on the bottom, so it actually gets flipped again. So it puts us the sine on the top and the cosine on the bottom. A double flip because tangent is sine over cosine, cotangent is cosine over sine, but it's on the bottom, so it's back to being sine over cosine. So now we're in a state that is, in my opinion, much easier to work with and find the derivatives and stuff with. And we are going to be doing derivatives because we can do L'Hopital's rule here. So we'll notice if we plug in 0 for x here, sine of 0 is 0. And we have an x here, so the bottom is also 0. We have an indeterminate form, where it equals 0 over 0. So we can do L'Hopital's rule and take the derivative of both the top and the bottom. So let's do that. My throat is getting raw because I'm just doing this entire exam really quickly. Derivative of sine of 3x is cosine of 3x, and then times the derivative of the inside, which is just 3. I can actually just put it there. all over, oh god, this will get long because it's a triple quotient rule. If you remember, a times b times c, derivative of that is a prime b c plus a b prime c plus a b c prime. Phew. So let's do this. We have a, b, and c. Cool. So a prime x, that's just 1, so cosine 3x times cosine x plus a times b times derivative of c, which is negative sine x, plus, this is going to be going on the bottom, plus a, whoops, actually on the last one, I accidentally did this part where you do c prime, so I guess with this bottom part now, we'll do a b prime c instead. So let's do that. I slipped up a little bit, but it's okay since these are all just pluses and it doesn't ruin anything. So um, a and then b prime. Oh god, this is a chain rule. So this is negative sine x and then times the derivative of the inside, which is just 3. So this is negative 3 sine x times cos x. Dang, that was long. And then well, now we're all done. We have our derivative of both the top and the bottom, and I'm praying, I'm absolutely praying that when we plug in 0 in for all of these x's, it will not be indeterminate and we can get our answer. So let's try that out. So this becomes 3 cosine of 0 all over cosine of 0 times cosine of 0 plus 0 times, oh, okay, I don't really have to worry about these at all since they have this times x term at the front and 0 times anything is just 0, so it's just plus 0 plus 0. Okay, so on the top, cosine of 0 is just 1, so this is just 3 all over 1 times 1, which is just 1, that equals 3. A, did I get the right answer? 7 or 8A. Let's go! I was so worried that plugging in 1 for or 0 for all of these x's would get awful, but thankfully it didn't. It crunched down very easily at the end. So, and then again, thinking back to the beginning, if you don't like secants and cosines and cosecants like me, just rewrite them as 1 over sine, 1 over cosine, 1 over tangent, things like that. It makes it a lot easier, at least for me. All right, question 9. I actually really like these problems. These like ambiguous function problems where it's like there's a couple unknown functions and it gives you a couple values for each of them, and then you're asked to like put some of them together and like do a derivative or whatever. So they're nice because they don't really have any calculations in it. You don't have to add and multiply and derive and all that. It's just referencing a bunch of these values and then maybe do some light multiplication at the end. So let's see what it's asking. We want we want big F prime of 14. So we need to take the derivative of f of g of x. So we can chain rule that. So this is now f prime of g of x times the derivative of the inside, so g prime of x. That's our derivative. Now we can plug in 14 for x for each of these. This is the fun part. You just keep looking back at those values that it gave you and sort of piece together what this should be. So this is now f prime of g of 14 is 2, and then times g prime of 14, which is 5, and then f prime of 2 is 12, times 5 is 60. So there's our answer. You can see why I like doing these. They don't take very long if you know what you're doing. All right, question 10. The slope of the line tangent to this curve at the point where y equals 2 is what? Okay, well to start, slope of the tangent line, that is keyword for take the derivative. So we should probably do that for this. Now taking the derivative of that normally would get very hairy because you'd have to get it in the form of like y equals, and we've got this y cubed and this xy squared. That wouldn't go very well if you try to get a y all by itself. So I think instead we'd want to do implicit differentiation. Now how that goes is you just kind of derive like normal, and whenever you sort of derive a y, you multiply it by dy over dx. That sounds a little weird, but when I go through it, it's not very complicated at all. So on the left here, derive y cubed. This becomes 3y squared. Now we just took the derivative of a term with a y in it, so now we multiply that term by dy over dx. So now we do everything else, minus xy squared. Okay, we have to do a mini product rule here. Let me write it up again. We'll try to nail it in all your guys' heads. AB, taking the derivative, gives a prime b plus ab prime. So this is now a prime, that's x, which is just 1. We just took the derivative of x, which is not y, so we don't multiply it by dy over dx. So now we have b, y squared, plus a times the derivative uh, of b, which is y squared, which is 2y, and we just took the derivative of a y, so we multiply this by dy over dx. And then that equals the derivative of 4, which is 0. So we've taken the derivative now. Um, Now we can plug in, now what we want to do is plug in values for x and y and then solve for dy over dx, and that'll give us, our answer here, our slope. The problem is that we only have a value for y. We don't have an x value. Really easy thing though, we can just plug in 2 into the original equation and get our x value if we solve for x. So we can do that. I'll do it off to the side here. 2 cubed minus x times 2 squared equals 4. So this is 8 minus 4x equals 4. 4x equals negative 4x equals, or negative 4x equals negative 4x equals 1. So our point now is 1 comma 2. We can plug in 1 for x and 2 for y into this and then solve for dy over dx. So this is now 3 times 2 squared times dy over dx minus 1 times 2 squared minus 1 times 4 times dy over dx equals 0. And now we solve for dy over dx. So looking back at the left, this is 3 times 4, which is 12 dy over dx minus 4 minus 2 squared, and then minus 4 dy over dx equals 0. Rearrange some terms. This becomes 8 dy over dx equals 4. So dy over dx equals 1/2 d. There we go, a nice implicit differentiation problem with a little hiccup where we didn't know our x value, but we can just find that easily by plugging in our y value and solving for x in the original equation. All right, question 11. Did I hit the record button? Yes, I did. Question 11. Just a derivative. Take the derivative of this. It'll get interesting with this arc sine here. So, derivative of arc sine, which is the same thing as sine or inverse sine. This is just sort of a memorization thing, something you gotta know. The derivative of the inverse sine is equal to 1 over the square root of, I have it up on my computer here. See, I don't even remember this stuff. This is so obscure. 1 minus x squared. Derivative of inverse cosine is negative 1 over square root of 1 minus x squared. And then the derivative of inverse tangent is just those two put together, one over the other, sine over cosine, like normal. So that's just a little thing that you might just need to know, because you might get questions like question 11 where you're asked to find the derivative of an inverse sine and you're screwed if you don't know what's going on. Um, so yeah, we know our derivative for that term now, which is 1 over the square root of 1 minus x squared. Now we can do the derivative of the left term. This is the same as 1 minus x squared all raised to the 1/2 power. So we need to do exponent rule and then chain rule. So this is minus 1/2 times this 1 minus x squared raised to the negative 1/2 power times the derivative of the inside, which is negative 2x. So there we go, we found our derivative. Now we just need to simplify. So let's keep the thing on the left, the beast on the left there with the square root, and then minus, okay, this 1 minus x squared to the negative 1/2 power is the same as 1 over the square root of 1 minus x squared. So we can rewrite it like that, like 1 over 2 times the square root of 1 minus x squared, and then times negative 2x, so that's like up there, times negative 2x. And let's actually change those plus those minuses there. All right, so now we're here. It looks like it wants us to punch these two terms into one. That's not too bad because we have pretty similar denominators. We can just multiply the left side by 2's to make them similar. So now it's 2 plus 2x all over 2 times 1 minus x squared. And we can also take out a 2 from each of these terms. And we're left with 1 plus x over the square root of 1 minus x squared, which is b. That was a long problem. Let me see if I got that one right. 11 is b. All right, cool. Yeah, so this one, I think it was really just testing if you knew your derivatives of inverse trig functions, which got the two main ones there, and then the third inverse tangent is just inverse sine over inverse cosine, so that one's also not so bad. And yeah, rest of the problem was fairly simple. Just, chain rule, exponent rule, yada yada. All right, question 12, the last one for this exam. It's just a derivative problem. Differentiate this. So, okay, to start, derivative of ln is very easy. It's just 1 over the inside. So 2x, and then we have to do the chain rule here. We have to take the derivative of the inside. Derivative of constant times x is just the constant, and then these square root 2's cancel, and we're left with 1 over x. What the hell? That easy? It's crazy. Why are they that easy on an exam too? You might think, oh my god, it was so simple, I did something wrong, but sometimes they just are like that, and they're benevolent instead of malevolent. So, okay, with that, exam 2 done, or exam 3 of the exam 2s. That's not confusing at all. This one was actually pretty not bad. A lot of these went pretty quick. The YouTube video will probably be like 30 minutes. But anyways, that was spring 2017 exam 2.